Alright, let's do a complicated example on the Laplace transform. So we are going to solve this initial value problem. So the idea is the same. So let me write that y of s is the Laplace transform of the unknown function y of t. And we are going to apply the Laplace transform to the left-hand side of our equation and to the right-hand side of our equation. Right? The Laplace transform of the second derivative is going to be s squared times y of s minus s times y of 1 and y of 0, and y of 0 is 1, so times 1 minus y prime of 0. Y prime of 0 is 0 plus 2 y minus s times 1 plus 5 y. This is supposed to be equal to the Laplace transform of cosine of 2t. So far we have calculated the Laplace transform of cosine t. But the way it works with Laplace transforms is actually whenever you want to solve some problem using Laplace transforms, you do not calculate it again. So it has been pre-calculated for you. And so in other words, you need to look it up in the table of existing Laplace transforms, right? And in particular, here the Laplace transform of the cosine function. Yeah, in this table, u of t, just ignore it. So u of t, pretend that it is not there. So the Laplace transform of the cosine function is going to be s over s squared plus omega squared, where omega is the frequency, right? And in our case, it is cosine of 2t, so which means we are going to have s over s squared plus 2 squared, which is s over s squared plus 4. So this is s over s squared plus 4. So this is the Laplace transform of cosine of 2t. Okay, now let us collect all the terms with y. I'm going to have s squared plus, they used to be an s here, plus 2s plus 5, everything with y. Then the right hand side is s over s squared plus 4. Then we have minus s in the left hand side, so I will write plus s. And also the right hand side, sorry, and this s is not here, so I made a little mistake, so is s y minus 1. And the left hand side has minus 2, so I will write plus 2. And so which means that our y is actually 1 over s squared plus 2s plus 5 times s over s squared plus 4 plus s plus 2. Right, and of course I am not going to calculate it myself, so I will just give you the answer that in partial fractions that you can do in Wolfram Alpha. You can check if I did it right. So far I've got s plus 8 over 17 times s squared plus 4 plus 8 over 17 times 2s plus 3 divided by s squared plus 2s plus 5. Wow. Right? So this is the Laplace transform of the unknown function. So question: how do we recover the original function? And then we just basically need to look in the table of Laplace transforms and notice that the patterns that we are looking for is 1 over something squared plus some other positive number, and here we have sine and cosine. Right? So notice the Laplace transform of the sine function and the Laplace transform of the cosine function. Sorry. And the other pattern is something where the denominator has s squared and 2s plus 5, so it looks like the sum of two squares. And here is the pattern is exponentially decaying sine wave and exponentially decaying cosine wave. Right, so these four patterns are going to be used in our Laplace transform. Okay, so let me continue. Alright, so our Laplace transform has the following terms. We're going to have so 1 over 17 times s over s squared plus 4, and its counterpart is also 1 over 17 8 over 17 8 over 17 times 1 over s squared plus 4. Right, so together these two they account for this term of the Laplace transform. So we have s over 17 plus 8 over 17. Right, so now I'm trying to rewrite it. This gives us immediately, if you check the table of Laplace transforms, then this immediately gives us 1 over 17 times cosine of 2t. This is a bit trickier because if you go to the table of Laplace transform, then the pattern is here is for the sine. If you look at the Laplace transform of the sine, then you have omega over s squared plus omega squared. But in our case, we have plus 2 squared, so omega is 2. So which means that in the numerator we must have 2. Right? So I'm going to rewrite it as 4 over 17 times 2 over s squared plus 4. So now that's exactly the pattern. So our omega is 2, and we have 2 over s squared plus 2 squared. Right? So this gives us 4 over 17 sine of 2t. All right, and then we have a more complicated pattern. So which is 8 over 17 times 2s plus 3 over s squared plus 2s plus 5. But I will rewrite it as how is it? S squared plus 2s plus 5. I will write it as s plus 1 squared plus 4. And 4 is 2 squared, right? That's the same thing. Because s squared plus 2s plus 5 is s plus 1 squared plus 2 squared. Yeah, right. Okay, but now, if you look back at the table of Laplace transforms, and you will see that we need to adjust it a little bit. So I will take out 8 over 17. And here, so notice that if we look at exponentially decaying cosine wave, then the pattern is exactly like this. So in the numerator we have s plus alpha, and in the denominator we have s plus alpha squared. But notice that in the numerator we must have s plus alpha. Right? So in our case it means that we must have s plus something. But since we have 2s, we really I really have to write 2. Alright, so then s plus 1 squared plus 2 squared. Alright, so let me look back at the table of Laplace transforms at exponentially decaying cosine wave. So we must have s plus alpha, and alpha is the same as in the denominator, and which is 1. So I must have s plus 1 here. Alright. But if I have s plus 1 here times 2, I have 2s plus 2. And originally I had 2s plus 3. So I need to account for one more. So it has to be 1 over s plus 1 squared plus 2 squared. Yes, sorry, let me rewrite it a little bit. Yeah, I'll write it here. S plus 1 squared plus 2 squared. Okay, now let us look at the table of Laplace transforms again. So this is the pattern for exponentially decaying sine wave. So if we look at the exponentially decaying sine wave, then the denominator is exactly like we want to be. So it's s plus something squared plus another thing squared. But now this omega, which is the frequency of the sine wave, this omega should be the same as in the numerator. So and currently our omega is 2, so which means I really need to write 2 here, so it fits into the pattern. But if I write 2 here, so in order to get it right, I have to divide by 2. And which means that, so now I'm practically done. So 8 over 17 times 2. This s plus 1 over s plus 1 squared plus 2 squared is exponentially decaying cosine wave. I think, yeah, exponentially decaying cosine wave, which means this is this is e to the minus t cosine 2t, and this one, the other summand, is 1/2 times the exponentially decaying sine wave, so it is e to the minus t sine 2t. Alright, done. Surely it looks a bit complicated, but if you recall how to solve differential equations, non-homogeneous differential equations by the method of variation of parameters, that one is is not easy either. So I'd say that both are pretty complicated. But anyway, so here we got the answer after very long computation and a lot of consulting with the table of Laplace transforms. The final answer is, in fact, these together. So let me maybe use this color. So it's going to be this plus this plus this. Yeah, I hope I did it right. I hope I haven't made any mistakes. But that's basically how it works. Yeah, and here I didn't even finish it. I didn't even type it, so I just wrote